Hello and welcome to this episode of Math with Martinez. In today's video, we are going to be describing symmetry of graphs of both even and odd functions. So let's go ahead and get started. There are a couple different types of symmetry that we will see as we are studying functions. The first type is what is called line symmetry. With line symmetry, the graph can be folded along a line so that your two different halves meet each other. Take, for example, this first one. We have some horizontal line symmetry across that x-axis. Do you see how we could fold along that axis and the upper and lower halves would be perfectly symmetrical? They would lay on top of one another if you folded it in half there. Or conversely, if we folded vertically in this graph along our y-axis, the left and right side there are perfectly symmetrical. You'll notice here that this point is the same distance away as this point. They are just opposites. They have the same y value, but their x's are opposite. This is a negative x and that's the positive x. Same distance away, but one is going in the positive x direction and one is going in the negative x direction. Same could be, well, kind of the same idea could be said here, except that they have the same x value, but opposite y values. One is a positive y value, some height that is above that x-axis, and the other is just the same distance away but going down instead. Now the other type of symmetry that we can see is what is called point symmetry. Oops. And with point symmetry, the graph remains unchanged when you rotate around a particular point. So let's say that this is the point xy. Well, what happens is when we rotate 180 degrees, then we'll get to the point where it is negative x and negative y. It would be the absolute opposite when you rotate around. Typically, what we're saying is rotating around this point right here in the middle, which is that origin. So let's move down here to kind of a synopsis. The x-axis and the y-axis are common lines of symmetry, and the origin, like I was just mentioning, is a common point of symmetry when you're talking about that rotational symmetry. Now, how can we test for symmetry if we don't have just the graphs to look at? It's easy to see when you have a graph, but how can we test for it otherwise? So our graphical and algebraic tests can be used to determine if the graph of a relation is symmetric to those big three, the x-axis, y-axis, or origin. So let's begin with our x-axis scenario. I'm going to take green for this. If we are working with our x-axis for every point x, y on the graph, then the point, what did we say above? It would be the same x, but the opposite y is also on the graph. And algebraically, how can we test that? Well, just replacing the y value with the opposite of y, and the result should be exactly the same. The result should be exactly the same. Now, what about for y-axis symmetry? For y-axis symmetry, for every point x, y on your graph, the point where you have the opposite of x and y is also on the graph, which we denoted in this picture up above. And so how can we test this algebraically? Well, just replace your x with the opposite input value, and you should have the same exact equation. And last but not least, what about this origin symmetry, that rotational symmetry? Well, for every point that we see x, y on a graph, then we should get the exact opposite x and opposite y also on the graph. And how can we do this? We replace y with the opposite of y and x with the opposite of x, and we should have the exact same equation. And we're going to do some examples where we see this play out. But let me now, before we move on, talk about the idea of an even or an odd function. It comes from looking at the types of symmetry. So from the types of symmetry, then we can know if we have even or odd functions. A function is said to be even if it is symmetric with respect to the y-axis. So that's our blue example up here. So a function is even if it is symmetric with respect to our y-axis. And what did we say the algebraic check was there? Well, to replace the opposite of x should give us the exact same function. So plug in opposite of x and you should get the same function back after doing so, after you simplify. And a function is said to be odd. Yep, this is if it is symmetric with respect to the origin. And how do we check this? Well, if we take our function at the opposite of x, we should get a function where everything is opposite of the original function. So now let's look and see here if we can take these ideas, apply the test to see if our function is even, odd, or if it is neither of those classifications. And then we're going to describe what type of symmetry we are seeing. Let's look here at example 7. We need to determine if this function is even, odd, or neither. I know this is a cubic function, so it has that really fun kind of shape to it. It's going to look something like this when graphed. But I don't know if it is exactly going to be that rotational symmetry like we see here. I'm not sure. We've got to check. So how do we check? Well, like we noted here, let's plug in the opposite of x and see just what happens. So I'm going to take my function at the opposite of x, do a little input here. That means I'm going to take opposite of x and cube it, and then I'm going to subtract the opposite of x. Let's simplify and see what happens here. When I take a negative and cube it, it's going to stay negative. It's going to be a negative quantity. And then when I take minus a negative, that's going to be addition. And so now let's look and see what happened here. This, ladies and gentlemen, it's the exact opposite of what we started with. Do you see how the first term was positive and now it's negative? And the second term was negative and now it's positive. This is what we call the opposite of our function. Every term has been made opposite. Let me move that actually because I want to write a little bit more. So every term here is made opposite. And so what does that mean? That means that what we have is an odd function. Therefore, this is an odd function. We've got some odd functions here. And what kind of symmetry is this? This is origin symmetry. Origin symmetry. I'm going to abbreviate symmetry to just SYM. So there we have it, y'all. We were able to use our test to figure this out. It is, in fact, going to be that like we saw up above here, where if we went and rotated our function, it would spin on the origin there. And every point in that first quadrant would reflect into the third quadrant with just the opposite x and y values. Cool. So let's look here at example 8 and see what happens in this case. Again, we want to take our function at the opposite of x. So this is going to be opposite of x squared plus 6. So what happens when you square a negative like that? What's going to happen there? Well, it's going to be positive. I still have the negative out front, but now this is going to be a positive x squared plus 6. Okay, so now compare it with what we had to begin with. What we had to begin with was exactly that. So this is the same function. This is f of x. So what we saw here is when we took f of opposite of x, we had the same function back. And so that means that what we have here is an even function. And even functions have that y-axis symmetry. And so if you think about that up here, that means that you could fold it along that y-axis, and on either side, it would be the same. Let's do a few more here. Let's look at example number 9. Again, how do we test the kind of symmetry? Well, you just go ahead and see what is my function at the opposite of x as my input. So opposite of x cubed minus opposite of x squared minus 2 times opposite of x. When I take a negative and cube it, it's going to be a negative output. And then it's going to be minus, well, when I take this, it's going to be minus this negative x. When I square it, it's going to be positive. And then the negative 2 times the negative x is going to be a positive 2x. Okay, now let's compare that with the original. I'm looking back to the original. The first term was positive and now it's negative. Was negative, oh, look at there, and negative. Okay, so it's not changing to where everything is opposite. It's not like we saw up here above where every term was made opposite. Only some of the terms are opposite. If that's what happens, then this is a case where it is none. It is not odd. It is not even. It doesn't have this y-axis symmetry, and it doesn't have this kind of symmetry. It's just a function that's cubic, but it's not going to spin around the origin like we see here. It won't spin around the origin. It's probably located a little bit off center. So there you see a case where it is neither. Let's look at 10 and try and discern what kind of function we have here, even, odd, or none. Neither. Oh, you know what? I should say neither because that makes more sense. Okay. Now let's go ahead and substitute in the opposite of x and see what happens here. That means we're going to have the opposite of x squared minus 4. All right, so when we square a negative, what happens, y'all? It's going to be positive. The second term didn't change at all. So what does that imply? What does that imply? How does that compare to the original function? It is the exact same as our original function. So this is that f of opposite of x equals f of x. So we have a even function. We have an even function, which implies that we have y-axis symmetry. Okay, we've got just two more examples that I want to look through with you, 11 and 12. Let's look at 11. Can you guys maybe try that one and see what you think? Is it an even, odd, or neither kind of function? Try number 11 and see what you think. All right, well, what we should have done is taken our function at the opposite of x, which is negative 8 over a negative x. But really, when we have a negative on top and a negative on bottom, that's going to be a positive. Okay, so is this the same or is it the opposite of our original function? It was a negative 8 over x, and now it's just 8 over x. This is exactly the opposite of what we started with. This is the opposite function. Yep, that pink kind of example from above, this will be considered an odd function. We could rotate it about that origin. That's where our symmetry is located. All right. Well, I've got one more here that I want to look at with you all and do together. This is an absolute value function. So let's see what happens here. If I take this function at the opposite of x, what's going to happen here? What's going to happen here? Think about this in the case of an actual value. Let's kind of do some little thoughts here. Let's say that our x, let's let x equal 3. Would we get the same result? Would we get, if we plugged in a 3 and we took the absolute value of 3 plus 1, it would be 4. But if we took f at opposite of 3, I'm doing this for this case because absolute value functions always kind of trip us up, don't they? Opposite of 3, that's opposite of 3 plus 1. Opposite of 3 plus 1, that's actually a 2, negative 2, but when you take the absolute value of it, it's just 2. Do you see how that is not, that is not going to be the same, and it's not the opposite value either? It's not like it's 4 or just negative 4 as the new output. This is a case where what we're looking at is a function that doesn't give us the original, doesn't give us the opposite. This is a neither case. So with these absolute value functions, you might want to check with an actual value for x and see at, like I did here, 3 and at negative 3, is it going to work? Really, I guess you could do that for any of these. You could just plug in a value for your x and then find the opposite value and see if it works, but I like to do it in general. That is all that we have for this video. If you had any questions, can you take a moment and share those with me so that I can have a better idea of how to address and give you that scaffolding that you need to be successful? And until next time, stay fired up, you guys.